Okay, welcome to part five, where this week we've been working on moving the AI rather than them being stationary and performing animations. Sort of the next level of complexity is to have them move about the world, and we need to figure out what the most optimal way to do that is. So this video is all about getting them moving around the world. It's a little bit of a different video. We're gonna step through kind of some of the learnings along the way to help people kind of understand how you prototype and develop logic rather than just jumping to the end state logic. So let's get started. The first decision we had to make is, okay, how are we going to move? We could move actors by lerping positions on the world. We could do a line trace and find ground and then basically move an actor to that point. That would be the lowest cost from a performance perspective. Or we could use any of the existing movement components. And so we played around with some different prototypes. And what we landed on is we don't need the character movement component. That's too heavy. It has things like gravity. It has position correction. It allows for keyboard input. It has a lot of things that we just don't need in our AI. And it would be overkill and a performance hit. We then looked at the nav movement component and found it to be too light. We would have to code too many things to make that work. So the happy medium was the pawn movement component. And actually what Unreal does is they provide you the floating pawn movement. So you can't actually use the U-pawn movement component. It has the floating pawn movement as a child that you can attach to your pawns, and it basically gives you no gravity, but it does allow you to move around on a nav mesh by issuing commands to the AI to move to a location, and it will path its way around obstacles, use the nav mesh, deal with any elevation changes on the nav mesh, etc. So the answer for us was to use the floating pawn movement as our movement component in the class. So we then set off to look at two different movement modes. The first mode is where we wanted to allow an AI to find a random location inside a radius. And we didn't want it to be too close. So if you think about this picture over here, we have a radius around the character that we're going to allow him to move to. But we also have an inner radius where we don't want the next movement. So if the actor is sitting here, if the AI wants to move inside this circle, we're going to not allow that. We're only going to allow them to select areas in the green so that they at least move this far and no further than this. And so right now it's just randomly picking the location this direction from around the player center. So I will move to a new location. The circle will move with me. I'll then pick another location and it'll move. So that's our random in radius. And the second one we wanted to do is have a predefined path, right? So we use a spline for that. So we're allowing the AIs to follow a path that we put in the level. And that path is being attached to the spawner. So the spawner will have paths on them that the AIs can then request and follow. So rather than having a path for each and every AI, it seems more logical to have the spawner control the paths, and then the AIs request that path from the spawner and follow it. This will play well into our overarching design when we start to have the spawner take more and more control of the overarching dynamics of the AIs. And so we started to build that out in our blueprint. So we're going to go look at that in a minute. But the essence for the random location in range is we basically find a random spot within a sphere. We have the character look at it. We draw our debug sphere on the ground, and we use the simple move to node to move the character. What we found is that there are 5 or 6 different move to nodes that give you different results. Because we want this to be as lightweight as possible and as simple as possible, What's working for us is the simple move to node. The actor then waits for a defined period of time, and the cycle repeats itself. So it basically calls itself and repeats that cycle again. The walking along the spline is a bit more complicated. So the first thing we have to look at is we don't know the length of the spline. However, we can retrieve that from the individual spline. So for example, this particular one, let's say that this length is 3,000 centimeters or Unreal units. Unreal units by default is centimeter. You can change that in the editor, but by default it's a centimeter. So this path is 3,000 centimeters. We also know what the pawn max walk speed is based on the pawn movement component. And so if we assume that the pawn max walk speed is 300 units per second, we can divide 3,000 by 300, and we can determine that it would take an AI 10 seconds to traverse this path. So by using that math, we can determine, okay, it will take, no matter what length I put this at, I can always compute how long it will take to traverse the path. So that logic is a bit more complicated. But again, we're prototyping in Blueprint so that we can get the reactions that we want. And then we'll optimize this as we move it into the C++ code. So those are the two methods. Let's jump in and kind of see how they're operating in the editor and give you a little bit of a flavor. We'll then do a little bit of a debug, and then we'll go look at the C++ code. Okay, so I'm recording this session a little bit halfway through my design process for the next chapter, and I thought I'd share where I'm at right now because likely all of this will be gone by the time I release the final video. And I realized I haven't really shared kind of how I prototype and develop certain capabilities. So for this, again, I don't even know if much of this is going to make it into the final video or the final solution, but it gives you a little bit of flair. What I typically do is, so I'm in the spawner. Actually, you know what? Let's go into the pawn. I'm in the pawn, and I've created these two functions here for perform path follow patrol and perform random patrol is the two things that I'm working on. And so I define these two C++ functions, and then I define the two parallel functions for blueprints. So these are blueprint implementable events. They show up in the blueprint with this name. They are prefixed with K2 to differentiate from the C++ version and the blueprint version. Then in the C++ file, the actual function simply punches out and calls the blueprint version. So I'm doing all of my prototyping in the blueprint, but I've set my logic up inside of this C++ function, which eventually all of the code will end up here, replacing this one line. And that is being called here. So if I'm doing a path follow, I call the C++ path follow, which I think I can get this all on one screen. Yeah. So if I'm asking to do a path follow, call the C++ path follow, which is here, which then in turn calls the blueprint path follow. Which means that in my blueprint actor, I'm a little tongue-tied tonight, when I launch this blueprint, I have my prototype code here. So I'm testing these two functions, the random patrol and the path follow patrol. And I'm basically using a bunch of blueprint nodes to rapidly iterate through different designs to try to get the result I want. And then once I get the result I want, I'll turn around and take all of this logic, convert it to C++, and put it back in the C++ file. So let's have a look at where we're at. What we're working on are these splines. And so the spawner now has these spline paths where we can define paths through the world, which are these lines here. So there's one that starts here, runs its way around like that. There's another one that starts here, goes up these stairs and back down, and another one that's doing this circle here. So these are my test patterns for getting a character to move. And then when I play, you'll see the characters moving up and down the stairs. There's a lot of work to still be done there. And the character following the spline path. So I'm testing various settings and changes to get these characters moving in the way I want them to move, all in Blueprint. So that I can sort of watch how that logic is executing in the code, debugging the various steps. And then once I've tweaked this enough that I'm happy with the output, then I will convert it all to C++. So again, I wanted to record this section, which I'll put in the video, because this is the process I go through in order to create some of the elements, but you only see the C++ version at the very end. I could go through 8 or 10 iterations in a Blueprint version trying to tweak it to get it to look better. So hopefully that's helpful. All right, this is another mid-development segment where I just wanted to share a few things on the way to the final product. So much of this design that you're going to see here will change, but I wanted to give you a bit of a perspective. So I'm in my level, and I'm working on getting the pawns to move around these splines. And the scenario I'm in is if I hit play, the pawns over here are moving just fine. You can see that the debug circle is moving in front of them, then they are moving to the debug circle, and this spawner is doing just fine. However, I have another one over here, and they're not moving at all. And I was perplexed and trying to debug this scenario. So that's where I'm at. What I've got set up is a couple of things. I can select this spawner here and turn it off, so deactivate it, so that this won't happen when I hit play in editor, so that I'm isolating away to just messages for that one. And then I'm going to turn on my pawn log. You know what? Let's put on our spawner too. Did I go to verbose? No, I did not. Verbose. All right. So both of those logs are on. And we're going to hit play. And what that does is none of these actors over here are running on their paths. So the only actor, or sorry, none of the actors over here are in the world. So I don't have to worry about that. And I could focus all my debugging on this individual one. And so if I look at the output log, we'll see that there's no active spline. That's the variable. Now watch what's going to happen. So the pawn was spawned in. It was given a skeletal mesh. It attempted to start the path follow, and then there was no active spline, so they can't follow the path. So this helps me isolate down exactly what's happening with this individual spawner, and so I can debug it a little further. Code-wise, there's a couple of things that are important. So here's the perform path follow routine where there's no active spline, which is the message that we're going to get is right here. So this is what I'm going to go debug. But what I wanted to show was in AI Spawner, this spawner activate, I've only got this in editor because you don't want to forget to turn this off and ship your game. So using the with editor forces this piece of code to only compile into the executable when we have the editor included. And at the same time in the C++ file, let me think, where is it? Start. Right here, I wrap the executable with the same thing. So the variable in the header file and the code in the begin play in editor allows us to not have those actors. And that's very beneficial because I wouldn't want to delete this and lose all the work of placing these spines. So rather than having to delete this to get it out of the level, I simply destroy it upon run, and then I'm only left with this one who is supposed to follow this path and wander through here and navigate their way around to the other side. So that's where I'm at. All right, so let's look at the path follow C++ code as we're converting it over from the blueprint prototype to the final code. So the perform path follow patrol, which we talked about, was just an empty C++ function that at the very end called the K2 version. So let's see what it looks like now. So the first thing we do is when we call the path follow patrol, sorry, let's get to the right spot. When we call the path follow patrol, if we don't have a spawner, we kick out with an error. We then start, here's our transferring the code from the blueprint. We get our spline from our associated spawner. If we don't have a spline, we'll kick another error. We determine the total time necessary to run the spline. So we get the length of the spline divided by the movement speed. That tells us how long it'll take the character to traverse the entire spline. And we say that we've consumed 0 of that right now, right? So we're at the front of this variable length spline that we're going to move at a certain speed. Once we've done that, we then kick off a timer, and that timer is going to call this particular function here every whatever we've defined frequency. So we have a frequency every 0.2, 0.3, whatever the case may be. We're going to tick this function, and then we're going to kick off any of the blueprint that might be left over. Here's the code in that ticking moment. So we basically every 0.2 check again that we make sure we still have a spline, determine if the pawn movement has been deactivated, which is like if we put the pawn back in the pool, one of the things we do is turn off pawn movement. So this will allow us to basically stop this timer from ticking and just clear itself out of the code. We then increase our time consumed by the frequency. So every time we're in here, we're increasing the amount of time we've consumed. We determine if we're going forwards or backwards on the spline. If we're going backwards, we do this. Not reverse. If we're going forward, we do this. If we're going backwards, we do this. Then we determine where we are on the location using the spline function get location at distance along the spline, which basically takes a float, which is where we are on that spline. We return in world space a vector. We draw our debug sphere at that vector. We set our look at rotation to that vector. And then we're kind of cheating a little bit here. If you look at the code for this simple move to location in the blueprint helper function library, there's a lot going on here. So rather than replicating this logic, you can see here it goes on for quite a few lines. rather than replicating all of that logic in our code, what we've done is we've included this blueprint helper library right here. So at the top, we've included this library. And sorry, probably path follow timer. And then we simply call that code right here. It's much easier than replicating all that logic. So that does the move to. And then we determine if we're done. So if we've consumed greater than or equal to the total time necessary to complete the path, we call our onFinished. And our onFinished will clear the timer, stop the ticking of the timer, and it will determine should we do nothing based on our structure. Should we return to the start? Should our character just go right back to the beginning? Like if you're in a loop, the end and the beginning are very close to each other. So if you're looping, you just do a return to start. Or do we reverse the direction? In which case we basically flip our reverse flag, set our consumption back to 0, and then basically reinitialize the timer again. So the only other thing I think is this look at, which is where we're basically setting our rotation between where the actor is looking and the target location, and then setting our skeletal mesh to that particular rotation, plus 90 because we didn't turn our mesh in our actor. If you have adjusted your actor, you may need to adjust that plus 90, but that allows us to get a forward-facing skeletal mesh in our actor. So that's the code right now that we're seeing running, and it was prototyped in Blueprint and now moved into C++. But now we have a moment where we're, upon reflection, is this the right way to do it? So now we're at an inflection point where we've got our Blueprint prototype working. We've moved it to C++. It's doing kind of what we want. But we're now starting to go, are we just making a behavior tree? Like, are we hard coding actions that a behavior tree would be better suited for? And from a design perspective, would these actions be better as tasks in a behavior tree? So that is kind of the aha moment we've hit at this video. And there's a little bit of a turning point here. So we have to ask our questions. Are we getting the performance we want out of our code? Would the behavior tree be more performant? Is there something inherent in the way the behavior tree works that might even improve our performance? Or is there going to be a cost to the behavior tree that is so high that we want to stick with our code? But our code doesn't feel very modular. It feels very bespoke. And if I need to add more and make more variants, it feels like we're going to get into sort of a spaghetti code environment. It doesn't feel like our design pattern is extendable. So we're going to pivot now and do some performance testing. We're going to actually code up a behavior tree and run some tests with our native code versus that code in a behavior tree. All right, so here we are in the native C++ code where all the actions are happening on the timer, and we're just running code inside each of the AI pawns to move them across the world. So they're chasing their respective spheres. Let's go ahead and start a log. And so we'll capture enough data for analysis of the native code running as a baseline. So that should probably be enough of a log file for us to get a feel for the performance of this set number of AI running with native code. So let's stop the log file. All right, and then we'll do a similar exercise by packaging up the behavior tree version and running the same test. So this is our single node simplified behavior tree. So maybe I should, let's open the other behavior tree first. Our first test of the behavior tree was to break each of the steps. So calculate the total time for the path, get the next location on the path, rotate the actor to orient to the path, draw our debug sphere, and then move our actor along the path and wait. And so we ran through this multi-task routine. What we then did is decide, you know what, let's see if there's performance improvements in putting them all together into a single node, which we did. And so that single node now looks like, does that launch it? Yes, okay. So the event graph for the single node says when we receive execution of our node, we're going to go get our tree keys off the blackboard. We're going to take our pawn and cast it to our AI pawn. We're going to calculate the total time to patrol in a function rather than a node. We'll get our next location to patrol, draw our debug, we'll rotate, we'll move, and then we'll save our values back to the blackboard, and then we just keep looping inside this one task. So we're basically looping inside one task. If the behavior tree does something and decides it needs to move off of this and break this loop, it can. And what will happen is, struggling today to get edges. What happens is this abort AI task will occur, which we don't have to do anything on because we're simply patrolling. But if we needed to clean up, exit, set some variables back, etc., we would do that on the abort AI track. But if the behavior tree doesn't abort it, so that this, since there's nothing else, so we could put a decorator on this and have it go target a player or do something different. But right now, basically, we go into this node and we're just cycling inside this node. And we've done all these basic functions, which again are just very exact same thing we did in the C++ code. We get our components, we move along our spline to a particular distance. Our draw debug is very simple. You're simply drawing a debug circle. Rotate finds the look at based on where the actor is and where the target location is, and then forces the actor to look at that location, etc. So that's basically how we've set up the single node behavior tree for our tests. So let's go see how that performs. Okay, so this is in a game client using the single node behavior tree. And I'll just press F8. Well, I guess I can't press F8 under the other. So each of the AIs are running towards or following their spline. Now, they're hitching a little bit. I still have some things to fix on the behavior tree cycling that they catch up to their target location. And so they're hitching a little bit as they get close. But as you can see, the same number of AIs are running. Instead of using my native code, they are now running the behavior tree code. And let's do a stat start file to capture some log data. All right, we'll just let that run for a few seconds, capture enough data so that we have a decent sampling of the data set as they move around. But as you can see in the upper right corner, we're floating kind of between 7 and 8 milliseconds on the game thread. So that performance level seems acceptable. We are, again, running the overhead we're running is the behavior tree on top of the code. It appears to be okay and would dramatically simplify our design. So our likely scenario is to go ahead and just do everyone that is not stationary have a behavior tree. That behavior tree can be super simple, like these guys just patrolling around the world, or can get more and more complicated. Obviously, the more complicated we do, the more cycles we're going to take out of the game thread. But I think we touched 9 there for a second. on the game thread. Anyway, that should be enough data. So we're going to do a stat stop file. All right, so that's this portion. Okay, so we're back in our editor, and now we're going to go look at our two session files. So we're going to go under Tools, Session Front End, over to the Profiler tab, and then load a file. And the file we're looking for is actually where we build. So let's just go to our temp folder, which is where our game build is, and under Saved, Profiling. These are the two we just ran today. So let's start with the native code. And we're going to take a look at, let's stretch this out a little bit. So you can see here, this is the game thread. And as I scroll across the game thread, the bottom line is 60 frames per second, 30 frames per second. So the native code is staying below the 30 frames per second, right? So we're bouncing around here as actions are occurring, but we're never touching the 30 frames per second line. Just one point here where we get awful close. Okay, so the native code, I would say, is just floating under the 30 frames per second. In the behavior tree, if we load that, we can see that it's slightly over the 30 frames per second. So there is overhead associated with, I'm not sure what that spike is. There is overhead associated with running the behavior tree. There are moments where we're crossing that 30 frames per second with the set number of AI running. So it is absolutely more expensive to include the behavior tree. So now it becomes a question of maintenance, expandability, ease of keeping the code clean. Is it worth it to have our own native patrol logic for the performance improvements? That's going to depend on everyone's individual game. That's going to depend on how many actors you think are going to be up and running in your world at any point in time, and whether or not you can afford it on the game hardware that you're targeting. So again, this is an older laptop. I'm running on 2018 laptop. So it's not like I have a lot of performance. This is not a server at all. So the added milliseconds are likely going to be worth it for us to continue using behavior tree just from a simplicity and cleanness of the code. But you may make a different conclusion based on your characteristics and what you need your game to do. But you can clearly see that there is a cost associated with running the behavior trees. It is not very significant if you're targeting a more high-end platform, but there is a cost, and you need to be aware of that. So hopefully this video helps you kind of think through performance tuning a little bit, when it makes more sense to look at simplicity and extendability versus optimizing code for performance reasons. Okay, so the conclusions. Based on the test results, the native code is more performant, which is kind of where I thought it would be. However, the behavior tree is much more extendable, even though it costs more CPU cycles. The big decision, I think, is how many AIs do we think is going to be in the world that are going to be pathing, but nothing else. Right? So if we have a lot of AIs that are ignoring the character and simply performing their routines and paths, those are probably worthy of the native code. However, if those AIs are going to interact with the player or perform multiple different actions, then it's probably more beneficial to have them in the behavior tree model. So for us, we think the extendability of the behavior tree is worth the cost. So we're not going to delete the code. So it's going to stay there in the pawn. And we might use it for things like birds and animals that are just there for kind of environmental aspects that might be moving around. But we're going to lean heavier into the behavior tree model for the rest of the video series. And the rest of these parts will be more behavior tree centric. We have our basic spawners working. We have our pawns using the object pooler. We've got basic animation and basic path following. So now we'll just transition into a bit more complexity in the behavior tree and a bit more interactions with the player. And then we'll wrap this series up. So once again, thanks for watching. We'll attach the code into the description of the video for anyone who wants to look deeper into the code. And yeah, so give it a like, a thumbs up, and we'll keep putting out videos. Thanks. Take care.